seminar. It's my pleasure to introduce Dr. Rimpei Chiba. He got his PhD from Oxford earlier this year, trying to find out the nature of dark matter using the bar of the Milky Way and its deceleration as a probe. And I'm looking forward to your talk.
Thanks for the introduction, and thanks everyone for coming to the seminar. So today I'll be talking about what the work that I did for my PhD thesis, which is to probe dark matter using the galactic bar. So the background image that you're seeing here is an image of a typical bar of the galaxy. This one's called NGC 1398. The linear stellar structure that you are seeing here is the galactic bar. And there is a number of evidence that the Milky Way, our galaxy, also has a very large bar at its center. And in the lambda CDM paradigm, we believe that each of these bar galaxies are embedded inside a much more massive dark matter halo. And the basic idea of my research is that these spinning bars will gravitationally stir the dark matter, and by this it will transport part of its kinetic energies and momentum to the dark matter, and as a result, the bar will spin down. So if we can somehow measure how fast this bar is spinning down, we can infer the existence of dark matter as well as its physical properties, like how much they exist or how they are moving. So first of all, let me describe the kind of motivation for why we need a new approach to probe dark matter. So as you know, the existence of dark matter has already been implied from several observations. Here, I'm just listing a few of them. The problem that I want to raise here is that most of the evidence of dark matter that we have so far only measures the gravitational mass of dark matter. Okay? We only measure the gravitational potential of a variety of systems using different methods. And then whenever we find any difference between the measured potential and the potential that we expect from the baryons, we attribute that difference to the existence of dark mass. Okay? But the problem of this is that basically any anomalies we find in the gravitational potential can in principle be explained by modifying the laws of gravity, right? Whether we can do this in a consistent way or not is a different question, but in principle, it's always possible because dark matter and baryons more or less occupy the same volume. So whenever we find dark matter, we also find some amount of baryons, right? So it's very difficult to completely rule out the possibility of modified gravity theories by just measuring the gravitational potential. Now, on the other hand, the galactic bars allows us a way to measure the inertial mass of dark matter. Okay. Now, the gravitational mass and inertial mass, they do take the same value, but conceptually they are two different things. Gravitational mass, on one hand, quantifies the strength of gravity that the matter generates, whereas inertial mass quantifies how much the matter gets accelerated when any kind of force is applied to it. Right. The reason why the bars can measure the inertial mass of dark matter is that basically the galactic bars gravitationally torques the dark matter, and as a result, the dark matter gets accelerated. And this acceleration is a measure of the dark matter's inertial mass. Now, of course, we cannot directly measure the acceleration of dark matter, but if dark matter is accelerating from the conservation of energy and momentum, then the bar has to be decelerating. Okay? And this spin down of the bar, which is generally known as dynamical friction, this is something that we could in principle measure. So here, I just want to clarify my point that the spin down of the galactic bar is only expected if dark matter exists in the universe. So the left part shows how the bars evolve in inside a live dark matter halo. So I'm showing how the bar's rotation frequency varies with time. So you can see that the bar's pattern speed dramatically declines from its initial value. But on the other hand, if you don't assume any dark matter and instead adapt MOND, from this red curve, you can see that the bar's pattern speed doesn't change at all. Okay? So these results imply that if we can find any evidence that the bar has been decelerating, we can use that as an evidence for the inertial mass of dark matter. And this is something that cannot be explained by modified gravity theories unless they kind of violate the conservation of energy and momentum in a very peculiar way. So in the first part of my talk, I will present two evidence for the spin down of the Milky Way's bar, one from the kinematics of the stellar disk and one from the metallicity of the stellar disk.
Can I ask you a question?
Yes.
On the analytic. Right. On the analytic dark matter halo. So there, when you say analytic, you really just mean just the dead profile that actually you're not, because presumably if it was fully analytic, you would actually, I mean, the reason that that's flat is because you're not, I think, and you can correct me if I'm wrong, you're not allowing that transfer
Exactly.
of energy and angular momentum between the bar and the halo. So in practice, it's really not the fact that it's analytic as much as the fact that it's what's it called, sterile or something.
Numerical analytic, but
Okay, so it's just that it's like a sterile halo.
exactly, you're using an analytical potential for the halo that is frozen in time.
Frozen.
Exactly. Yes.
Thank you.
And so then similarly, sorry. So then similarly, you know, for your Mond curve on that same plot, you know, is the reason why it's not spinning down also just that in this Mond curve, there's no other dynamical degree of freedom besides like the baryons?
Yes, so in the Mond simulations, there are baryons, but there's no dark matters. The amount of baryons is much smaller than dark matter, so the baryons are not enough to make the bar slows down. Basically.
Yeah, like, but in some modified gravity theory with some, you know, dynamical degree of freedom, like some scalar field or something, is it obvious that, you know, that a similar spin down wouldn't happen?
Yeah, so this uses the classical Mond theory. There are also simulations that use the relativistic version of Mond, which also shows that the bar doesn't slow down. But I'm not aware of any Mond kind of theories that makes the bar slow down, actually.
Okay, great, thank you.
Up on that. Basically, like in a Tevis or something, you're thinking that you would actually be able to have this transport to the field. What is the like what would be happening in that case? Like it's less obvious to understand how, like, what's a kind of physical instantiation of that.
Yeah, no, I agree. I mean, well, like, so in Tevis, I guess, right? You know, so there's this extra vector field, which is a dynamical degree of freedom, and then it functions like dark matter does, right? Yeah, you know, and so then similarly, I just imagine that for some like arbitrary modified gravity theory, you know, where there's some extra degrees of freedom besides the baryons, you know,
like that's an interesting question. Like, could it be some weird vacuum density or something funky going on, right? Because it's just you're basically just putting that into you're taking it out of the bar and putting it into the field. So you could have some, you know, well, I mean, I think the question is if you have, I mean, you have to have a particular model. In this case, in Tevis, it's not, you know, it's not like a particle.
Well, does it have inertia? Is it associated with modification?
I don't think so. I'm not a Tevis expert.
Start to keep this kind of interesting discussion for.
Apologies, Renvin, not Renvin.
Okay, so the basic idea to kind of identify the slowdown of bar would be to answer the question, if the bar has been spinning down, what kind of impact would that have on the motion of stars? Because motion of stars is something we can actually measure. So to analyze the motion of stars, first, let me describe angular action variables. So on the left, I'm showing an orbit in the XY plane where you can see that their position and velocity are kind of changing in a not so simple manner, right? Which means that XVs are not the best coordinates to work on. And actually the dynamics becomes very trivial if we level these orbits with integrals of motion, which simply means conserved quantities. The action variables is just one of the integral motions, but they also serve as a canonical momentum. So in the 2D axiometric case, we have two actions, the angular momentum J phi, which basically characterizes the size of the guiding orbit, and the radial action, which basically characterizes the extent of radial motion around the guiding orbit. Okay. And the coordinate that is conjugated actions is called angle variables. So theta phi basically describes the phase of the guiding orbit, and theta r describes the radial phase around the guiding orbit. So you can see that by using angle action coordinates, the orbits that were rather complicated in real space turns into a very simple straight line in angle space. Okay, so now I will turn on the bar. So on the left plot, I'm showing the orbits in the bar's rotation frame. So the bar's lying on the x-axis, and the black circle that you're seeing here is the so-called co-rotation radius. This is the radius where the circular frequency of the orbit matches the bar's pattern speed. So you can see from this blue orbit that whenever the stars are close to this co-rotation radius, it can become resonantly trapped. And when they become resonantly trapped, you can see that they are kind of oscillating back and forth the bar's minor axis. Okay? So their phase is locked. And this is in contrast to the untrapped orbit, which is freely circulating around the bar. Okay? So now when we view this in the action plane, you can see that for the untrapped orbits, the actions are roughly conserved, whereas for the trapped orbits, they show a very large oscillations in the actions. So for these untrapped orbits, these old actions that I introduced earlier, they are no longer conserved, even to first order. But there are different types of actions that these untrapped orbit approximately conserve, and these are called the fast action and the libration action. Fast action essentially is just a linear combination of the old actions, and basically it just describes where the orbit is trapped along the resonance line. And then the action of libration basically characterizes the extent of librations around the resonance. Okay. And this is defined in the so-called slow angle action space. So in this phase space, you can see that the orbit is revolving around the resonance.
What is the dot dashed? Is that the outer?
Resonance.
Okay, I just wanted to make sure that's.
So for most of my talk, I will concentrate on the co-rotation resonance. So in this case, whenever you see this slow angle action space, you can interpret this slow action as just angular momentum divided by 2, and the slow angle as the azimuthal angle times 2. Okay. Right. If you have questions. No,
I do. I'll wait though because
okay.
a lot of your time. So.
Right. Right. So now I want to make the bar slow down. So I need to have a model for the bar's spin down. So regarding the bar's pattern speed, you can see that N-body simulations typically show that the bar's pattern speed doesn't decline linearly, but it's slowing, like kind of gets smaller over time. And actually a good fit is given by a 1/t law. And if I adapt this 1/t function, the dimensionless slowing rate, which is defined as omega p dot over omega p squared, this becomes a constant. Right? So I can kind of conveniently parameterize how fast the bar slows down with just one parameter. Okay. And then as the pattern speed declines, the co-rotation radius of the bar expands over time. And then simultaneously, the length of the bar also increases. And you can see that the ratio between this co-rotation radius and the bar length is roughly constant. So I will model the radial profile of the bar's potential such that the characteristic length for this potential gets longer in proportion to the bar's co-rotation radius. Right? So I'm keeping this constant. Okay. And then finally, I fit my model to a separate hydrodynamic model, which was constrained using inner gas kinematics, and then determine all the 3 parameters. Okay, so now I'm going to make the bar slow down. So now you can see that as the bar slows down, the co-rotation radius slowly expands towards the outer galaxies, the resonance moves towards large angular momentum, and you can see that these orbits are dragged along with the resonance. Okay? And the reason why they are dragged along with the resonance is because they have to conserve the fast action and the libration action. Right? So you can see that they are kind of remaining on the same ring in this phase space. Okay. So from this, we can already imagine that if the bar has been slowing down, then it would have had a dramatic impact on the distribution of the stellar disk. So now we want to see how this effect appears on the motion of the stars near the sun. So on left image, I'm just showing again the image of a barred galaxies. We know that the position of the sun is roughly here, around 30 degrees away from the bar's major axis. And on the right, I'm showing the velocity distribution of the stars that passes near the sun, which is measured by the Gaia Space Telescope. So in this velocity space, you can see that there's a lot of structures. In particular, the biggest structure is this group of stars at low azimuthal velocity, which is clearly separated from the main distribution. And this group of stars is called the Hercules stellar streams. And if the galaxy is completely axisymmetric, then we wouldn't expect these asymmetric structures to form in the velocity space. So the fact that this Hercules stream has been interpreted as made by some non-axisymmetric component of the galaxy, in particular the galactic bar. So here I want to explain a bit of history of how people try to interpret this Hercules stream. So the first explanation of Hercules was given by Dienen, who kind of associated this Hercules stream with the so-called outer Lindbergh resonance. So this is a resonance when the orbit finishes 2 radial oscillations around when it goes around the bar once. And if the outer Lindbergh resonance is very close to the sun, then the bar has to be very short and must be rotating very fast at a pattern speed of around 50 to 60. But then in the recent decades, this fast bar model came into tension with measurements directly from the inner bar regions, which measure that the bar is much longer and rotating at a much slower pattern speed at around 30 to 40. And then in 2017, Villegas proposed that if we adapt this low bar model, then the Hyperstream will be associated with the co-rotation resonance of the bar. But you can see that their model is less convincing than the fast bar model because it doesn't create this sharp bimodal structure. And I can show that if the bar has been naturally slowing down, this problem is naturally resolved. So here I'm going to show my test particle simulation of the stellar disk, which is perturbed by a slowing galactic bar. So you can see that as the bar slows down, the resonance of the bar sweeps through the solar neighborhood one by one. This one is the outer one-one resonance. This one is the outer ring bar resonance. And then it's followed by the minor resonances. And then finally, the co-rotation resonance arrives. Okay. So now when I compare the result of a slowing bar model with a constantly rotating model at the current pattern speed 35, which is favored by observations of the inner bar regions, you can see that even if the current bar parameters are exactly the same, whether the bar has been slowing down makes a significant difference. And in particular, for the constantly rotating bar, we don't see any structures, but this black curve basically marks the boundary of the co-rotation resonance. So all the stars that are inside here are resonantly trapped. So there's a lot of trapping happening, but because the distribution of stars inside the resonance is smoothly connected to outside, it cannot reproduce the Hyperstream. But on the other hand, if the bar has been slowing down, then this resonance was originally at a very low angular momentum where the phase-space density is much, much higher. So the resonance will capture stars at that inner dense regions. And then as the bar slows down, the resonance will bring these dense patch of stars to the solar neighborhood. So you can easily create this bimodal structure. So when you compare these models with the data, you can see that the data clearly supports the slowing bar model. So this was the first kinematic implication that the bar has been slowing down.
How fast?
So it's slowing down. So it depends on the initial pattern speed. But for example, if you take the initial pattern to be 70, like twice the value, then it's going to be slowing down in around 5 giga to 35. Take the initial pattern speed to be larger, of course, it will be much longer.
Well, I'm just wondering if you can define it. Can't you just define a time scale as omega p over omega p dot?
We can do that as well, yeah.
And so then that time scale is like
my model, I'm keeping omega p dot over omega p square constant, which means that omega p dot over omega p would be varying. The time scale would be changed over time. Yeah. Yeah. But sorry, I don't have the number right now. Yeah.
I was wondering if any fine-tuning is defined by this model. And so the slowing down time
Yeah.
compared to the age of the galaxy.
Yes, exactly. But in the next. So let me give a brief theoretical explanation on what happens. So here I'm showing the Hamiltonian of an orbit that is subject to a slowing bar. You can see that it really resembles that of a pendulum. So we have a kinetic term that is quadratic in momentum and the sinusoidal potential term. But you can see that we also have an additional term that is linear in the angle with a coefficient s, which basically is called the speed parameter, which essentially describes the slowdown rate of the bar with respect to the vibration period of the trapped orbit. Okay. So when s is equals 0, we have this phase growth that is exactly that of a pendulum. When s is non-zero, then the potential gets linearly tilted. So the amount of trapped phases kind of get contracted. If I further increase s, the trap volume further decreases. And then at a critical point when s is larger than 1, then the potential no longer forms a local minimum, which means that none of the orbit can be trapped in resonance. So physically, this means that if the bar is slowing down too slowly, the resonance will sweep the phases too fast, such that none of the orbit can catch up with the resonance. Okay. And then because I'm working in a disk dynamics, I can use epicycle approximations. And in this case, the speed parameter reduces to the ratio between the slowing rate and the bar strength. So I did a simulation with wide variety of bar strengths and bar slowing rate. And you can see that as predicted by theory, if the bar strength, if the bar is too strong, or if the bar is slowing down too slowly, then this parameter is going to be too small, such that the phase space is going to be dominated by resonantly trapped stars.
Just real quick, you
Yes.
didn't really define the bar strength. It's the potential depth of the bar compared
Yes,
to.
kind of, yes. Yes. Measureless kind of parameter for that. And then on the other hand, if you go to the left top corner, so if the bar is too weak, or if the bar slowing rate is too high, you can see that the trap volume is too small, such that it cannot reproduce the Hyperstream. So given a bar strength, this means that this bar have to be slowing down in a moderate rate. It cannot be too fast, it cannot be too slow as well. So I quantified the agreement between my simulation and the data. And then by taking the strength of the bar, which is constrained from a separate study, I estimated the bar slowing rate. And on the right part, I'm kind of comparing my measured slowing rate with anybody's predictions from and anybody's simulations, which is particularly tailored to the Milky Way galaxy. So the two red point here assumes MOND and modified gravity. So in these models, you can see that the slowing rate is very small, and this is more than 2 sigma offset from a measurement. Whereas if we assume cold dark matters, we do have a lot of scatters based on the kind of computational method or like the initial conditions, but generally they're consistent with my measurement. Okay. Now, all my analysis so far was based on the assumption that the Hyperstream was made by the correlation resonance. Okay, but the problem of this assumption is that the kinematic features of the Hyperstream were also reproducible by other perturbations of the galaxies, like the spiral arms or the merging satellite. Okay, so by just looking at the kinematics, it was difficult to conclude whether the bar has actually been slowed down. So next, I decided to look into the metallicity of the Hyperstream, because the metallicity directly indicates where the stars were born. Basically, the higher the metallicity, the more closer to the galactic center that the star was born. So if the Hyperstream was made by the correlation resonance of the bar that was migrated from the inner galaxy, then it should be significantly metal rich. Okay, so I compared the metallicity of each stars by fitting their colors and magnitudes using stellar isochrons. So for those people who are not familiar with stellar isochrons, isochron is basically a curve in the color magnitude diagram that represents a population of stars that were born at the same time from the same gas but with different initial mass. So depending on the initial mass, you end up having different colors and different magnitudes, and the isochron is just a curve that kind of connects those points. So the top panel shows how this isochron varies with the metallicity. So basically, metallicity have two main effects on the appearance of the star. One is that metallicity hampers the nuclear fusion of hydrogen, so it makes the stars look dimmer, but also it kind of hampers radiative transport, so it makes the stars swell up and look redder. So you can see that if I increase the metallicity from blue to white, you can see that the isochron is shifting right to the red direction, but also downwards towards large magnitude. Okay. And then on the bottom panel, I'm showing the dependence on age, which you can see that the isochron only depends on age on the bright hot end, which basically just means that the color and magnitudes of the main isochron, main sequence stars, doesn't change for most of their lifetime as long as they're not too massive. So this means that as long as we avoid these two massive stars, we can accurately estimate metallicity from just the position in the color magnitude diagram. So I tested this method using open clusters, because open clusters, we have a measurement from spectroscopy. So you can see that apart from a constant offset, which is mainly due to binary contaminations, my measurement is in agreement with literature values. So I use this method to compute the metallicity of each star, and then I compute the mean metallicity in the local velocity space. So the left is density, the right is mean metallicity, and they're both overlaid by the contours of the libration action in black and the fast action in blue. So you can see that the Hyperstream, which is fitted by this correlation resonance, is significantly metal rich, which indicates that these stars originate from the inner galaxy. But the fact that the Hyperstream is metal rich itself is not a new finding. This has been known as early as 1970s. So I decided to look for more decisive evidence of the bar slowdown from the distribution of the metallicity inside the resonance, not when compared to outside.
Just ask the question.
Yes.
That plot.
So naively, it looks like the metal-rich stars are not librating around the stable fixed point in that thing's a resonance contour essentially there, right? The bottom, the dark curves, the black curves, right?
Yes, but the thing is that, so yes, so this is the contours of the libration actions, but you have to compare the same fast action as well, right? If the orbit is if the two orbits are in the same place, you have to compare, for example, this one with the same one. So you have to compare this and this. You cannot compare this with this here or anything. You cannot compare this with this.
Okay.
Because they have different fast actions, and metallicity also depends on fast the radial action as well.
Okay.
So to understand how the metallicity is distributed inside the resonance, we first need to understand how the resonance gets populated. Right? So here I'm going to show how the resonance evolves as it sweeps through the stellar disk. So you can see that as the resonance moves towards large angular momentum, right, you can see the y-axis moving down. You can see that it simultaneously grows in volume. So it sequentially captures the surrounding orbit. And once these orbits get captured into the resonance, they conserve the action of libration, which essentially characterize the distance to the resonance center, right? Which means that the order of the capturing is preserved inside the resonance. Right? The red stars, which were captured earlier, they always occupy the core of the resonance, whereas these blue orbits, which were captured recently, they occupy the surface of the resonance.
So can you go back to the previous slide? One said that most of it was captured recently by that same argument. The high metallicity stuff.
Yes. So yes, the thing is that it is due to the look at the really at the core. Look at the really at the core of the resonance. That's the long branch. The kind of surface of the resonance. Yes, yes, but we could. I will show later that we could still see a gradient in metallicity. So basically, the bar resonance develops just like a tree ring. Okay, so in a tree ring, like a tree, waves appear at the bark of the tree, and basically, it records the climatic condition of that year. So, for example, if the amount of rain changed, or if there was a forest fire, those changes and events will all be recorded inside a tree ring. And basically, the same thing happens for the bar's resonant phase space, because first of all, stars can only enter the resonance from the surface, right? The stars cannot immediately pop up here. That violates the Lewis theorem. And then once they get captured into the resonance, they conserve the action of vibration, which are these green contours. So basically, we can use the distance to the resonance center as a kind of chronometer to infer the bar's evolutionary history. And in particular, if the bar has been slowing down, then these stars, which were captured earlier at the inner disk, they should be more metal rich than these stars, which were captured recently at the outer disk. Right? So we should expect a monotonic increase of metallicity from the surface towards the core of the resonance. Okay, so now, as I already discussed here, when we do this, we have to be a bit careful because the metallicity not only depends on the libration action, but also depends on the radial action, right? So basically, stars are born on near circular orbit with small radial actions. And as time passes, it interacts with other stars and giant molecular class, so it gradually gains radial motions, right? So stars with large radial actions are on average old, and because they are on average old, they are also on average metal poor. So that's why we see these metal poor stars at the rim of the velocity space. So when we want to see how the metallicity varies with these libration actions, we have to follow one of these contours, which is a bit difficult to do here. So on the right, I converted the coordinates. So now the x-axis is the libration actions, the y-axis is the radial actions. So here you can clearly see that metallicity increases towards small radial actions because stars get younger, but also towards small libration actions because they were captured earlier at the inner disk. Okay. And then if I just subtract the metallicity gradient in the radial actions, we can much more clearly see how the metallicity increases from right to left. Okay, so now here I'm just showing the mean metallicity as a function of libration action. So I just converted the 2D plot into 1D statistics. So you can clearly see that the metallicity is rising. And then on the right, I applied exactly the same analysis to my mock data that is generated from my simulations. So the black curve is when I use a slowing bar, the blue one is when I use a constant bar. So you can see that this upward trend in metallicity is only expected if the bar is slowing down. So the fact that we do see this upward trend in the data kind of proves that the Milky Way has been slowing down. And as I explained in the beginning of the talk, the slowdown of the bar is only expected if dark matter exists. So this result kind of implies that dark matter is a real thing. And from the amount of increase in metallicity, I can also estimate that the pattern speed have declined at least 24 plus minus 6%, which is already in 2 sigma tension with MOND, which only predicts the pattern speed to fluctuate at most 10%. Okay, now in my analysis, I have been assuming that the bar's pattern speed is 35. Okay, and then with this, the co-rotation resonance precisely matches the Hyperstream, and therefore I looked into the metallicity gradient inside the Hercules, and I was able to conclude that the bar has been slowing down. But the thing is that there is still some uncertainty in what the value of the pattern speed is. So I decided to do the analysis by reversing the logic. So now I would not assume anything about the bar's pattern speed, but instead I would just assume that dark matter exists, and therefore the bar has been slowing down. Okay, and if this is true, this will require the metallicity to increase towards the core of the resonance. So I can use this as a requirement to constrain the current pattern speed. And I have to check that the result that I get matches the original assumptions. So basically what happens if I change the pattern speed is that, for example, if I lower the pattern speed, basically the resonance moves up in velocity space, okay? So now if I compute the metallicity as a function of libration action, you can see that it starts to undulate, which is not what we expect from the slowing bar model. If I increase the pattern speed, now it moves down. Now we can see that the separatrix is now crossing through the metal-rich region, which means that we have to give like separate explanation of why metallicity is rich here and why it is metal-rich outside and why is it symmetrically connected. So this is also inconsistent. So I did this analysis for a wide variety of bar pattern speed and bar strengths, and then I computed the likelihood of the data given the models by kind of demanding a monotonic increase in metallicity. And then again, by taking the bar strength from a separate study, I estimated the optimal pattern speed to be 35.5. And then on the right, I'm showing how this compares with measurement from other studies, which you can so see that my measurement is in good agreement with estimation from the stars and gas in a bar region. Okay. So here you can see that these red points here are the ones that are measured using a local stars before the slow bar model came out, right? So before, everyone was believing the fast bar model, and so they estimated the pattern speed to be very high. But then once we have had a lot of data from the inner bar region, we started to realize that the bar is much more slower. Okay, now in the latter part of my talk, I will discuss about how we can use this bar's slowing rate to learn about the nature of dark matter. So this is still an ongoing project. So I would just describe the kind of overall picture and describe what kind of tools that I have developed so far. So here I'm just showing the equation motion of the bar. This equation basically just tells us that once we have a measurement on the bar's slowing rate, by multiplying it with the bar's moment of inertia, we have an estimate on the total torque that is applied to the bar. If we subtract the contribution from the baryons, we can estimate the strength of dynamic friction by dark matter. And the significant thing about this is that dynamic friction not only depends on the spatial distribution of dark matter, but it also depends on the velocity distribution of dark matter. Okay? And the velocity distribution is something that cannot be constrained by just mapping the galactic potential. Okay? And this velocity distribution is particularly important from the perspective of the direct detection experiment, because the velocity distribution that is passing through the Earth basically directly affects the interpretation of the experimental result, right? Because basically in experiment, we are just measuring the recoil energy, right? So for example, if we want to infer the mass of the dark matter, we need to know what velocities they are coming in. And currently people are just assuming that the velocity distribution is Maxwellian. They're assuming that it is isotropic, and it's assuming that the halo has no net rotation, right? But none of these assumptions are justified, right? So my aim is to use the bar slowing rate to give constraint on the main kinematic parameters of the distribution function of the dark matter. Okay. So to do this, first, I need to have a good understanding on how dynamic friction depends on the kinematics of the halo. So for the rest of my talk, I will be discussing about how to model dynamic friction. So dynamic friction is conventionally modeled using linear perturbation theory. So this equation just formulates the net exchange in angular momentum between the bar and the halo, and it is derived based on the so-called linearized collagenous Boltzmann equation. So that's why it's called linear theory. And the validity of this linear theory hinges on two factors. One is, of course, the amplitude of perturbation, which in the case of the bar, it's mostly okay. But the second one, which is much more important, is how fast the bar slows down, okay? And then if the bar is slowing down fast, which we call the fast regime, basically it has been shown that linear theory can explain the simulations remarkably well. And this is basically because if the resonance is sweeping too fast, then because the nonlinearity always develop at the resonance, if the resonance is moving fast, then there would be no time for the nonlinearity to develop. So linear theory becomes valid for a long time. But on the other hand, in the slow regime, where S is smaller than 1, linear theory fails quite badly. And to illustrate this, I computed the torque in the slow limit, which is the case where the bar is just constantly rotating. And you can see that linear theory on simulations agrees only for the first few 100 mega years, which is just few orbital periods.
That's basically the libration period.
Is exactly, yeah, exactly. Yes, so the problem is that from my measurement, we know that the real bars are actually evolving in this slow regime, right? So we cannot use linear theory to model dynamical friction. So the reason why linear theory failed is because of resonant trapping, which is essentially a nonlinear phenomenon. And so to model these nonlinear effects, I use the so-called method of averaging. So the basic idea here is that near the resonance, there is some kind of slow nonlinear evolution going on, which is described by the slow angulation variables. So we want to model these variables. And when we model these variables, we can essentially ignore all the other fast motions. Okay? So formally, this means that we are going to replace the Hamiltonian with that is averaged over the fast angles. Okay? And if we do this, the average Hamiltonian would not depend on the fast actions or the fast angles. So the fast actions will be exactly conserved. So essentially, the method of averaging allows us to reduce the problem from a 60 phase space to a 2D phase space. Okay. And in the case of the slow limit, where the bar is rotating at a constant rate, the Hamiltonian will be constant, which means that we have 3 integrals of motion, right? The Hamiltonian and the 2 fast actions, which means that the system is integrable. Okay. And if the system is integrable, we can find a set of angular action coordinate, where the actions are all exactly constant. So if we use these coordinates, the collision-Boltzmann equation will have a trivial solution, which basically states that we can get the phase space density at any point at any time by simply just winding the angles backward in time. Okay. So here I'm going to show how the phase space density evolves in this nonlinear regime. So basically, before the bar forms, right, you can see that the phase space density increases towards low angular momentum. Once the bar forms, now the orbit starts to move along these contours of the true actions. And because the frequency of oscillations kind of dropped towards the spiratrix, what happens is that the phase space gets mixed like this, okay? So they get mixed both inside and outside the resonance. Now, if I compare this result with my simulation, you can see that they are in good agreement. Okay? So now that we know how to model the distribution function, I can use this to compute the dynamical friction by just multiplying it with the torque on a single orbit and then integrating it over the entire phase space. Now, these integrals, I cannot do it analytically, but if I do it numerically, I can reproduce this oscillating behavior of dynamical friction. Okay. Now, the good thing about distribution function is that it can be used to kind of derive a variety of quantities, right? So for example, if I integrate it over the velocity space, we can get the density response as well. And this is really kind of useful to understand how physically dynamic friction is actually working.
Just to double check,
Yes.
we're still using
The S equals 0 limit here,
S equals 0.
not allowing the resonance to move.
Yeah.
Even though we know that it has been moving.
Yes. So the reason why I'm using slow limit is because I can get an analytical solution to it. Yeah. So the top panel shows the time evolution of the phase space density, which I've already shown you before. And then the bottom panel shows the corresponding response in the real space. So basically what's happening here is that in the phase space, we see that this dense regions originally moved to the right, it moves up, and then it moves down and it phase mixes, right? This is what we observed, right? Now the center of libration here corresponds to the bar's minor axis, and these pi and minus pi correspond to the bar's major axis. So the initial movement from here to here basically means that the mass is moving from the bar's minor axis to the bar's major axis. And that's why a wake is created. And then you can see that this wake is lagging behind the bar, which means that they are pulled by the bar. So that's why it is gaining angular momentum. And then afterwards, after a half a libration period, it passes the center of libration, which is the point where the density wake passes the bar's minor axis. it goes to the other end of the bar. Now it starts to pull the bar in the forward direction. It makes the bar accelerate. And that's the reason why we have this change in the sign of the torque here. And then gradually, as the phase mixes, the density wake becomes asymmetric around the bar, and then dynamic friction vanishes. Okay, but as Lauren pointed out, the work that I've been doing is limited to the slow limit, which is the case where the bar is constantly rotating, which is obviously inconsistent because whenever we have a non-zero torque, the bar has to be decelerating. So basically, the bar's evolution can be divided qualitatively into 3 regimes. Okay. So slow limit is the case where I've already shown. In this case, the system can be approximated by an integrable one, so we have an analytical solution to it. For the fast regime, there is no nonlinear trapping happening, so we can use linear parameter theory. But unfortunately, real bars evolve in this slow regime, this intermediate regime, where we don't have any analytical approximation to the equation measure, so we have to do it numerically. But the thing is that the averaging method still works. Okay, so this doesn't hinges on the speed parameter. So instead of kind of simulating the 3D equations of motions, we can just use the average Hamiltonian and just solve the equation of motions in this slow angular action space, right? So that's why I call this the 1D average model. And you can see that the 1D average model describes the summations remarkably well. So what you're seeing here is a combined effect of the resonant dragging and the phase mixing that is continuing inside the resonance. And then similar to what I did in the slow limit, now that I have the distribution function, I can just integrate it over the velocity space to get how the density wake looks like. So here I'm just showing the density wake that is created individually by the 3 strongest resonances, the co-radiation resonance, the auto-radial resonance, and the so-called dialect radial resonances. So you can see that each resonance creates a different types of density wakes. And then if I just superimpose these 3 strongest resonances, I get this picture. And then the middle row shows the density wake that I calculated using a 3D particle summation. So here I just integrated the entire halo and just sampled the particles that came close to the galactic plane. So you can see that my model kind of captures most of the features that we see in the simulations. And then the bottom panel shows the residual between my model and the simulations, which you can see that we have these residuals that is localized in space. So these are some kind of density wake that is created by a resonance that is not included in my model right now. Okay, so essentially, if I just include more and more resonance, I can make my model much more better. Okay, so so far I've just developed these methods to model dynamic friction. I haven't actually investigated how dynamic friction depends on the kinematic parameters of the halo, so that I'll keep it for my future work. So to summarize my talk, the basic idea of my research is that if we can find any evidence for the slowing bar, we can use that as an evidence for the inertial mass of dark matter, and this cannot be explained by any modified gravity models. And then I have shown that the bar's evolutionary history is recorded inside the resonance, just like tree rings. And we can read out this information by looking at how the metallicity varies with the action of vibrations. And then when I applied this data, I will like this theory to the Gaia data. I found that the correlation resonances shows a metallicity that increases towards the core resonance, which strongly implies that the bar has been slowing down. And finally, I proposed that the bar slowing rate can not only be used to prove dark matter, but can also be used to prove the nature of dark matter. Okay, so in the context of the lambda CDM models, this allows us to kind of constrain the kinematic properties of the halo. But I will also mention that dynamic friction also depends on the quantum properties of dark matter. For example, if dark matter is a degenerate fermion, which is forming a degenerate core at the inner galaxy, or if dark matter is forming a Bose-Einstein condensate at the galactic scale due to having very small mass, then essentially dynamic friction is predicted to be weaker. So in principle, the slowing rate that I have measured can also be used to test these exotic dark matter models. Okay, thanks for listening.
You seem to have assumed that the metallicity distribution of the galaxy has reached some fixed distribution before the bar starts slowing down. Is that reasonable?
So basically, we predict that the metallicity gradient is established in the first few gigayears.
but stars keep on
Forming. And how stable is that?
So the function of it's just a function of it's just rises slowly in the latter part, very old. But then you might be able to see like a drop in metallicity at the core of the resonance. Or might have been slower.
Metallicity doesn't grow as fast as you might think. It starts off, goes real quick and then it goes very slowly.
But I'm wondering if they move the way that they're out on data depends on what the metallicity is.
I don't know.
You can say that.
I mean, basically, you're looking at things like, alpha over Fe versus Fe over H. That's the way you constrain that, right? But I don't know how well it's really constrained at this point.
Focus on that. Halo, very well.
Yeah, but we want to know stuff down in the center, exactly. And I don't think that,
Yes.
so, but while I had the microphone, so you said that you could rule out MOND at the 2 sigma level. What would have to improve to do better than that?
Right. So basically, I think it depends on which kind of data I use, but no. How much metallicity has been increasing, right? But the thing is that, as you can see from my model predicts that the metallicity increases around 0.16, which is like twice as large as the data, right? Which indicates that actually that there is some stellar diffusion going on, right? So this means that if we can model properly the stellar diffusions, we can probably expect the metallicity to be much larger. And in that case, we could probably increase this tension more.
And how would you check if you're doing the diffusion correctly? Are there any chemical signatures, like I say, alpha over Fe, for example, which would give you another handle on how
Yes, so essentially that's how people do it. So they look at alpha of F and how that works. So they look at alpha of F and how that correlates with the
So this might be an obvious question because I
right. So first question is why does bar forms basically? It basically the understanding is that first spirals forms, right? So spirals form from linear instabilities, and then as the amplitude of the spirals increases, then non-linear trapping happens at the interlinear resonance. So these stars start to self-gravitationally combine each other, and it forms a bar basically. That's the kind of understanding. And so what was the next question?
saying this bar formation is an irreversible process, and then that can only go in one way.
So you said that is the formation of bar a reversible process?
Yeah, continuous process. But what you're describing seems to be like
Yes, basically the evolution of the bar. Slow down and get longer.
Why are only half the galaxies formed?
Why only half galaxies? I think one is because if you look into like the how to say the infrared, the amount of bar fractures increases, right? So I think that's one thing. But yeah, I think it's maybe because a lot of anybody simulations just model the evolution of the stars, which violently creates these bars. But maybe if we include more gas inside, it would weaken the formation of the bar, because the gas will essentially give angular momentum to the bar, right? So it slows down the evolution of the bar. So that might be a reason. Yes.
A very nice talk, Rimpei, and I apologize. I'm I'm a rough shape after only a few hours of sleep here, but I thought that I saw some structures in that Gaia data. Can you just go to the kind of,
So
no, the grayscale. Yeah, that's what I'll do. So if I look at, if I look at this overall structure, kind of from your model, I expect that separation, and you can kind of see all of those resonances like the tree rings, but there's also lots of other structures in here that are not just kind of explainable from that. And is that, do you look at that and say, wow, there's a lot of other dynamics going on here? Or do you look at that and say, there's a lot of selection effects going on here? How do I understand, some of those other little metallicity clumps, and are those prior events, or what are those?
these metal clumps are open clusters, so we know these ones. So we also see some kind of dense patch of kind of groups here. So these kind of like delta-like function-like structures are probably open clusters and so on. But yes, we also see these kind of arc-like structures above the resonance, which
Open clusters actually a dynamical phenomenon? I never thought about them that way, but your talk is inspiring me to think about them that way. Is that?
confined in phase space.
Yeah.
So that's why we do see it as a blob.
Sure.
And of course, open clusters essentially is expected to dissolve after that.
Yeah. People don't really have a great sense of what. Right. So globular cluster is like kind of thought of as like a, thing. An open cluster is a concentration in phase space, and it has a metallicity as well. That's kind of, but actually is an open cluster a structure, like a structure in, like, is it a dynamical structure, or is it like, is it better to think about it that way or not? Because people have always been talking about like dissolved open clusters. They use this terminology of cluster to, refer to other substructures that are clusters, but actually, should I be thinking about those open clusters as dynamical phenomena only?
Gravitationally bound, because they're not.
Yeah, they're not. That's what I'm saying. Yeah.
They're have more gravity. They're yellow background.
Sure, but my point is do we actually understand the origin of those open clusters dynamically?
Just star clusters that started out in a.
But did they actually start it as and I'm asking, yeah, that's for sure true.
This is partly why I was asking about the metallicity, because there's evidence structure here that's associated with connection to metallicity star condition. And so I guess I was asking, how can we be absolutely sure? Well,
So
that some of this structure in metallicity is
so I think
as an origin of the overall structure of the galaxy evolving versus continuing star condition.
so that basically we can break the degeneration by looking at the age distributions. So if you look at the open clusters, their age distributions is very much narrow. Whereas if you look at the Hyperstream, it is broadly distributed.
Okay, so now age plus.
So it's not considered to be an open cluster.
What is the age spread in a typical open cluster?
Less than years.
Okay, so they really are delta functions in,
So that's
okay.
actually a question. Did you work out the mass of those two red blobs? What is it? It's like the biggest cluster we've seen there, like 10 to the 5 solar masses. Is that enough to show up in this plot? If you weren't checking. Right?
Yeah, I need to check, like, so whenever I make the bins, I need to make sure like what the fraction of the stars in this bin corresponds to the open cluster.
Yeah.
I haven't done that, but given that it shows a clear signal, I think it is dominating it, yes.
Well, if they do have the same age, then they formed in the same place and they were originally gravitationally bound.
Yeah.
And then they should have.
I mean, my question was just more generic about all the other substructures there, not specifically on the open clusters, but I mean, to the extent that open clusters are, kind of.
Everything.
Well, they're a thing, but they're kind of not a thing too, right? They're, Oh, is someone drawing? Oh, do we have a, oh, okay.
That was me. So is that what you're talking about?
Zoom bomber.
So there's a feature there above the 0, 0 that shows up in both plots. So what's that?
These ones, you mean?
Yeah, that's
The underdensity, Peter, or the overdensity?
No, there's an underdensity
Density.
where the red thing is, which of course demarks an overdensity. And then it's also a lower metallicity, it's green.
Yes, so basically, from the dynamical perspective, we don't expect these kind of blobs to appear just here. We only appear the structure to be like an arc-like structures. So, for example, I can just no, oh yes, skip. So I have a very crude model for how the metallicity will look like in the for my model. So you can see that if the outer window resonance has been kind of sweeping as well, it does create this low metallicity structures that is kind of just below the outer window resonance, which does kind of resembles the structure that we see here. So, I mean, this structure is called the hat structures, which is kind of thought to be associated with the outer window resonance. But you can see that my model predicts the position of the hat to be a bit larger, which kind of indicates that I have the wrong rotation curve, basically. So I'm assuming a flat rotation curve here, but if I make it slightly negatively inclined, the position of the resonance will kind of shrink. So I think that these hat structures can be explained by the outer resonance, both the kinematic structure and the chemical structure. But these kind of blobs that we see here is probably not explainable just by the bar.
So the Hercules stream, which I attributed to this slowing bar and driving a bunch of stars outward resonantly, the fraction of stars in the Hercules stream, can that be informative in the sense that could that also tell you the capturing probability into this resonance and
So
the bar slowing speed as well?
you're saying that instead of looking at the metallicity, I should look at the phase space density, you mean, inside?
Let's say there's a million stars in the Hercules stream versus a billion stars in the Hercules stream. That's got to tell you how fast, how capable the bar is
Yes.
in capturing resonances.
Basically, you know, when I was doing these simulations,
Like the map. Like the map.
when I was matching my simulation with data, my simulation with data, I was basically just
Comparing the peak amplitudes. You're just comparing the height between the two peaks. Is that what we're doing?
fitting the overall structure. Yeah.
The bar die? And if it does, what happens to the galaxy after?
Buckles, but it doesn't die. Buckles, but it doesn't die. So the let's give the final. Let's give the, which case it cannot be overblown. It cannot be overblown. Indistinguishable. I'm not sure if that is the origin of it. Become violence.
Yeah, there are people who will claim that our Milky Way bulge is a buckled old bar. I mean, I don't know if you are partial to those claims, but
Yeah, so one of the origin of the bulge is
There's a
that
difference between bulges and most spirals and the bulges, what I call them elliptic. Right, they're different kinematic orbits, so they don't look like they're formed the same way.
Yeah.
Yeah, that's the claim, and I think that's fairly believable.
basically
And you've already waited 5 billion years. You haven't got that much time. Right? I mean, well, actually, did you try to estimate the age of the bar?
Age of the bar. So age of the bar depends on what kind of initial pattern speed I assume. So it's hard to kind of give estimate, but yeah,
Give an estimate, yeah, okay.
What about dark bars?
dark bars do. I mean, stars and dark matter are just similar collision-less systems. So there have been shown that in anybody simulations, the dark matter can also form a bar-like structure. So it kind of makes the potential of the bar kind of more deeper. Yes.
Is the dark bar, should I just think about it the way I think about it, like the dark matter halo around like, is it also kind of bar-y? I mean, is it with the baryonic bar, in other words, like, is it bar within a bar, or is it?
It is not as thin as the baryonic bar, but it's more round, but it is a bar and it exists in the scale as the same as the baryons.
Are there more questions or from the online audience? Okay, if not, I think we can thank Rimpei again and close.